Okay, so for today's lesson, we're going to continue our conversation about determining equations of lines, and we're going to look at some special cases where lines have some special properties that we need to make sure that we take a look at. So to start off, hopefully you saw in the warm up, I was hoping that you would take these four graphs and use your knowledge of how to sketch lines and plot these lines on each one of these graphs so that we can look at some of the characteristics of the line. So hopefully you've done that already, and then we can take some time now to take a look at what we saw. So first off, I'm going to look at the first two graphs, graph 1 and graph 2. And when you graphed those lines, so I'm just going to switch this to single page, this is what you should have got. So starting off with the y's, we had y equals 3 and y equals negative 10 on graph 1. And I just wanted you to note here that, usually we write lines in the form y equals mx plus b. And you'll notice that neither one of these equations has an x in it. And that means that there's going to be a 0 in front of the x. So that means that the slope, or the m value, is going to be 0 over 1 because we don't see the x there. And that just leaves the constant term. And we know that the constant term is always the y-intercept. So if I want to graph y equals 3, I know that my y-intercept is going to be 3. So I'm going to put, first of all, I make sure I label my graph. So I have my x-axis horizontally, my y-axis vertically, and I just put the 1-to-1 scale here so that the reader knows that I have a 1-to-1 there. So I'm going to start with my y-intercept at 3. And then I'm going to rise 0 and run 1. So I'm going to rise 0, 1, run 1. Rise 0, run 1. Rise 0, run 1. And you can see that it creates a straight horizontal line because the slope is 0. It's not rising, it's not falling, it's just 0. So it's flatlined. The way that I like to remember it is that if I have the line y equals 3, that means that every single y value on that line is equal to 3. So you can see if I have a point at like negative 3, the y value is going to be 3. If I have a point at negative 10, the y value is going to be 3. If I have a point at 5, the y value is going to be 3. So it's just basically saying every y value of your graph or of your line is going to be 3. So that's what it looks like. Okay, same thing goes here for our y equals negative 10. So we can think about this as being the y-intercept is negative 10, and we can think of this as having a slope of 0. So I'm going to rise 0, run 1, rise 0, run 1, rise 0, run. So I get this flat horizontal line. Or we can think about it as every y value on our graph having a value of negative 10. And if I look along here, no matter what x value I choose, the y value is always negative 10. Okay, so when you have something that's just in the form y equals a number, that is always going to form horizontal lines because we know that the slope is going to be 0. Okay. The x graphs kind of break all the rules here because every line that we've studied basically has the form y equals mx plus b. However, this has no y in it at all. So it breaks the rules. And it breaks the rules because instead of having a slope of 0 like this one does, the slope is actually undefined. Okay? So if I think about this the way that I thought about this, if I have x equals 3, that's basically saying that every single x value on my line is equal to 3. So if I have a y value of 0, my x value is 3. If I have a y value of 10, my x value is 3. If I have a y value of negative 8, the x value is 3. So no matter where I choose my point, no matter what I have for my y value, the x is always 3. And that creates that vertical line that breaks the rules because the slope is undefined. We've got 0 run on the bottom of a fraction, just doesn't work. And then we've got the line x equals 3. And then along the same lines here, if I think about what x equals negative 10 might look like, every single x value on this line is negative 10. So no matter what y I pick, I've always got the x of negative 10. And again, it creates that vertical line. Okay? So what we wanted you to see there then is that we've got special cases of lines in this example. And the special cases in this case create our vertical lines and our horizontal lines. And for our horizontal lines, they're always in the form y equals, and whatever the y value is on that line is going to be what your y equals. So this one here would be y equals 3, y equals 1, y equals -2, y equals -4. So it's got a slope of 0, a rise of 0 over 1, and it's in the form y equals a number. Vertical lines are going to be in the form x equals a number. So this would be x equals -5, x equals -3, x equals 1, x equals 3, x equals 5. The slopes are undefined because it's got a rise, but it doesn't have a run, and you can never have 0 at the bottom of a fraction. So we've got undefined slopes for all these. It breaks all the rules, and that's why it looks different, x equals instead of y equals, compared to every other line that we talk about. Okay? So that's those are two special cases. We've kind of talked about them in the past, but I just wanted to formalize that a little bit, the horizontal and vertical lines. And in the second two graphs that I asked you to look at in the warm-up, we see two other special cases. So when we look at those graphs in a little bit more detail, so for graph number 3, I've got my graph of the 3 lines here, my blue, my green, and my pink. And when I graphed these lines, what I noticed is that they were all parallel to each other. So when I drew the lines, I noticed that they never crossed each other. And even if I extended them forever in either direction, backwards or forwards here, I can visualize that these are never going to cross with each other because they are parallel. And when we look at their equations, we notice something that they have in common. If you look at the m value, or the slope for each one of these lines, the slope is 3. So the blue one is 3x plus 4. There's our y-intercept of 4, and then rise 3 over 1. The green line is -8 as the y-intercept, rise 3 over 1. And the pink line doesn't have a number there, so we assume it's 0 as the y-intercept, rise 3 over 1. And because the slopes are the same, you can see that the lines are parallel. And that is a characteristic of all parallel lines. Parallel lines, if you write it in the form y equals mx plus b, you will see that the slopes are identical. Okay? If there's any variation in the slope, then you can imagine it's going to tilt a little bit one way or the other way, and eventually those lines would cross. But when they're all the same, they're never going to cross each other. Okay? And this one's a neat one too. Graph number 4. I had you graph the lines. So the purple one right here is y equals 3 over 2x plus 2. So I put my y-intercept at 2, and then I went up 3 and over 2 to come up with another point, and then I sketched my line through that. And then my second line was y equals -2 over 3x plus 2. I decided to stick my negative up top so that I had a negative rise, which is really a fall. So when I graphed that, I started again at the y-intercept of 2, and then I went down 2 over 3, down 2 over 3 to get my line. I drew my line through it, and when I drew those two lines together, and a neat property occurred. It was I noticed that the two lines met each other, they intersected each other at 90 degrees. And when two lines intersect each other at 90 degrees, we call those perpendicular lines. Okay, so these two lines are perpendicular lines. And if you look at their slopes, there's actually a neat property here. So first of all, I want to point out that in order to be perpendicular, you have one that has a positive slope, so going up to the right, and you have one that's going that has a negative slope going down to the right. So you have to have one positive slope and one negative slope. So the slopes in our lines have opposite signs. One's positive when one's negative. Okay. The other thing that you can see when you look at the slopes a little bit more closely is that 3 over 2 is the reciprocal of 2 over 3. So remember, we talked about reciprocals when we were dividing fractions. And when we divide fractions, you always multiply by the reciprocal. The word reciprocal just means flipped, okay? So if I have 3 over 2 as my fraction, the reciprocal of that is going to be, if I flip it, the denominator becomes the numerator and the numerator becomes the denominator. So the reciprocal of that is 2 over 3. So when two lines are perpendicular to each other, they have a neat property that, first of all, their signs are opposite. So one's positive, one's negative, and the slopes are reciprocals of each other. So they're flipped. There's flipped versions of each other. And we call those negative reciprocals. So if we have parallel lines, we have slopes that are the same. If we have perpendicular lines, lines that meet at 9 degrees, there's slopes of those two lines, or however many lines you're looking at, are going to be negative reciprocals of each other. Okay? So just to summarize, I've got some pictures here. So for parallel lines, again, I've just shown you two other examples of parallel lines. So this is y equals 3 over 4x plus 1, and y equals 3 over 4x minus 3. And if you look, what is the m value of this one? 3 over 4. What is the m value of this one? 3 over 4, just those numbers in front of the x. And you'll notice that they are the same. So I always do a little bit of a mental checklist here. So parallel lines have slopes that are the same. So if I'm looking to see if two lines are parallel, I am looking in my head, I'm going to do a little checklist. Are the slopes equal? If they are, then they're parallel. And if they're not, then they're not parallel. Okay. Perpendicular lines. So here, I'm just going to zoom in so we can see those numbers a little bit better. I've got the line 2x plus 3. And I've got the line y equals negative 1/2 x minus 1. So you can see them drawn here. And you can see that they cross at 9 degrees. So if we look in a little bit more detail at the slopes, I've got a slope of 2, and I've got a slope of negative 1/2. So first of all, this one is positive, this one is negative. So that's check number 1. The slopes are opposite signs. And then we look to see if they're reciprocals of each other. So this is a slope of 2, which I would describe as 2 over 1. And if I flip 2 over 1, I get 1 over 2. And you'll notice that this slope is 1 over 2. So two or perpendicular lines, perpendicular meaning that they meet at 9 degrees, have slopes that are negative reciprocals of each other. So in my mental checklist, I'm looking, first of all, are the slopes opposite signs? Is one positive, one negative? And second of all, are the slopes reciprocals of each other? So are they flipped fractions? And if both of these boxes are checked, if there's opposite signs and reciprocals, we know that the slopes are negative reciprocals, and we can then conclude that the lines are in fact perpendicular. Okay, so the slopes hold the key. If we want to figure out, actually for all of these special lines, if we want to figure out if a line is a horizontal line, the slope would be 0. If we want to figure out if it's a vertical line, the slope is going to be undefined. If we want to figure out if they're parallel lines, then we know that the slopes are the same. They're equal to each other. And if we want to know if they're perpendicular lines, then we look to see if the slopes are negative reciprocals of each other. Okay, so those special lines, or those kind of ones that we wanted to focus in on, contain special properties within their slopes that give them some connection. Okay, so just to do kind of a quick little check here, how can we tell if two lines are parallel or perpendicular? It's not always in our best interest to have to graph the lines, because if we might not have graph paper, or we may not have time because graphing takes time. The nice thing now is that we have the power just to quickly look at the equations and make some conclusions about those lines. So for example, if I look at this first set of lines, I've got y equals 3 over 2x plus 5 and y equals 3 over 2x minus 10. If I look at those slopes, 3 over 2 is the same as 3 over 2. Because they have the same slope, I can conclude that these are going to be parallel lines. Okay. For the next set of lines, I have y equals 3 over 2x plus 5 and y equals 2 over 3x minus 10. So when I look at those slopes, first of all, I can see that they're not equal to each other. So I can rule out the possibility of them being parallel. I know they're not parallel, but they might be perpendicular. So how can I check that? So first of all, if they're perpendicular, they're going to have opposite signs. And when I look at this one is a positive slope, so it's going to go up to the right. But this one also is a positive slope going up to the right. So I know they can't be perpendicular because their signs are not opposite of each other. I don't have one going up to the right and one going down to the right. So I can stop right there and say that these are neither parallel nor perpendicular, even though they have slopes that are reciprocals of each other, they're not negative reciprocals of each other. And that's the necessary condition for it to be perpendicular. Finally, if I look at these two lines, I've got y equals 3 over 2x plus 5 and y equals negative 2 over 3x minus 10. Again, I look at it first. The slopes are not the same, so I know it's not parallel. So I want to check to see if they're perpendicular. Well, I've got this one that's positive, this one that's negative. So there's our first check in the checkbox. They're opposite signs. And then I see this is 3 over 2. This is the reciprocal 2 over 3. Those two fractions are just flipped. So that checks the second box of my checklist. So I can conclude then that they are going to be perpendicular. If I were to graph them, they would meet at 9 degrees. And I know this because the slopes are negative reciprocals of each other. They have opposite signs and the fractions are flipped. Okay, so now we can start to visualize what's going on between sets of lines a little bit more clearly without having to actually graph those lines.